Uh, my name is Carlos Thompson, okay? Professor Carlos Thompson. I'm a PhD. YouTube, Carlos Thompson channel on YouTube. Okay, today is February 22nd, 2025. I would like to send you a message, important message, about theory of relativity. First of all, theory of relativity we can split in two branches. One branch I call special relativity, SR, and the other branch is general relativity, GR. Okay, special relative, we have a flat space-time. This is the dimension of this space. Is a 4-dimension, and I will derive just assuming a time-like trajectory. What this means? This means that the coordinate of the time coordinate will be negative and plus for a spatial coordinate. Okay, this type of trajectory I will also mention when I talk general relativity, okay, Einstein Field Equations. Okay, here in space-time, the flat space-time in special relativity, you can find on this link https://carlosthompsonphd.com.br, and there I will guide you to access more than 100 products, I would say. And if you have some question, please email me, cafthompson at gmail.com. Cafthompson, C-A-F Thompson, gmail.com. Now, in this flat space relativity, I have a product, okay, is mentioned in this link, that I will have 60 videos talking about, in detail, okay, about the special relativity. So, today I will dedicate more in general relativity, okay, Einstein Field Equations. This is very, very complex subject, only because the math, the applied math. Okay, I would say the applied math in curved space, again, the time-like trajectories, I will split in manifold, okay? And manifold, I will derive every derivation will be refined in detail. I'll talk about intrinsic geometry and tensor in curvilinear coordinate, okay? Any curvilinear coordinate. And the space will be the 4-dimensional space, exactly the same space-time in special relativity. Okay, the Einstein's idea about EFES, okay, Einstein Field Equation, is very, very, very simple. The partial differential equation, nonlinear, also you can write, okay, like G, capital G, okay, is a covariant derivative, okay? This is equal, this is a constant, this is the energy, momentum, stress tensor, okay? This is called Einstein tensor, okay? Capital G is Einstein tensor. This capital G here is the universal gravitational potential, okay? This is derived from Newtonian limit, okay? Everything will be recorded in detail, okay? Just to show from where it came, this relation. It's a very, very, very important. So, the complexity will be, I'm talking about the math, intrinsic geometry, I repeat, and tensor theory, curvilinear tensor theory. In R4, what means R4? Is a four-dimensional space-time. All the steps in the derivation will be carefully in detail, okay? Will be detailed, all the steps, just to lead in the final, this partial differential equation, is Einstein Field Equation. And also there, I'll talk about Schwarzschild theory, which is a special case of Einstein Field Equation, just to set the energy, momentum, stress, tensor in this case, will be zero. So this will be the equation, simple equation for the Schwarzschild theory, which is very, very important, okay, in the relativity theory, general theory. I would like you, please, give me a like or dislike and share and make a lot of comments what I'm talking about, okay? So I will end of this my introduction to the study of general relativity, okay? Just saying again for you, don't forget, okay, to mark, like, dislike, and share with your friend, okay, and groups. And don't forget to comment. This is a very, very challenge, okay? That's general theory of gravity. I would like just to emphasize that the math, the applied math to the special relativity is simple. It's very simple, okay? High school students could follow the math applied to the special relativity. But, on the other hand, Einstein Field Equation, which can written in a simple way, what is complicated, very, very, very complicated, is the math, intrinsic geometry, manifold, and tensor theory, in general, curvilinear, okay? That's it. And then I will also emphasize a very, very, very interesting words that I'll raise here for you. And don't forget this message, okay, that I write over here, which is as follows. It's a very, very important. That's a few words. I would say, look how interesting. Space-time tells matter how moves. On the other hand, matter tells to space-time how to curve. This simple tensor explain clearly why we are right. Is equal a constant k, I'll put there, t mu, where k is 4 pi g and also just for curiosity, okay, k is derived assuming weak field approximation, okay, and Newtonian limit. That's how we can get this constant k. Everything, okay, just for you to understand, I have much more than 500 page written just to waiting for my recording, okay? Thank you very much. And again, I will insist, please, don't forget, like,